Ed. At this point, I'd like to recognize our coalition partners. These are the people that have the table set up outside of the auditorium, and thank them for coming. We have with us tonight Environment Colorado, Alliance for Climate Education, the Healthier Hospitals Initiative, Conservation Colorado, 350.org, Clean Energy Action, and Coloradans for Fair Rates and Clean Energy, also called CoForce. So we want to thank them for coming, and please take some time to speak with them, find out what they're about, and pick up some of their handouts and information. So thank you, coalition partners. Okay, so I think we're ready to move on to our first technical speaker.
Can I say one more thing?
Yeah, sure.
I forgot a key piece before the technical guys start. With this clinic today, they have twice the space and half the energy costs. That's what smart building, energy efficiency, renewable energy, it's great for our planet, it's good for their bottom line, and it makes us a healthier place. So I'm sorry, that was the key, that was the clincher of the whole thing, and I forgot it. Sorry.
Thanks, Ed. Okay, all right, so let's move on to our first technical speaker. This is Chuck Kutscher. Chuck is a PhD in mechanical engineering from the University of Colorado. He's currently principal engineer in the concentrating solar power section at the National Renewable Energy Laboratory. Chuck served as chair for the Solar 2006 National Solar Energy Conference that took place here in Denver. He's also editor of a 200-page American Solar Energy Society report called Tackling Climate Change in the U.S. He writes a monthly climate change column for Solar Today magazine, and he's authored over 70 papers and book chapters, so he's not busy at all. And Chuck is a really excellent communicator of climate science to the lay public, so he'll have some really good information for us tonight.
All right, thanks very much, Jim, and thanks to all of you for coming out tonight. I've got about 20 minutes, and what I'm going to cover is basically the reasons why this is such an urgent problem, why we really have to address it, and we have to address it with all haste. If you watch television, you read newspapers, people might get confused. There's a lot of misinformation about climate change. We have people saying it's a hoax, it's exaggerated. Now that's in the popular media. If you look at the scientific journals, if you look at Science and Nature, those two are probably the most prestigious general scientific journals that we have. The Proceedings of the National Academy of Sciences, or the work of the Intergovernmental Panel on Climate Change, which reviews all of this work and about every 6 or 7 years publishes the summary of it. There's no disagreement. If you look at the scientific journals, it's clear climate change is happening, we're causing it, and it's very, very serious. And so I guess that leaves open the question for, most people do not read scientific journals, so most people aren't trained in science, engineering, that sort of thing. So, is there, some popular media, a professional source that one can go to get the truth? And I did find one, and I'll show it in the next slide. If you read The Onion, it says, report global warming issue from 2 or 3 years ago may still be a problem. So, and I think that's why we're here, because we realize that, yeah, it may be a problem. Melting the polar ice caps maybe is something we should be concerned about. So I'm just going to very quickly review the science. Now the skeptics will tell you, oh, you can't believe those computer models. Actually, the computer models have gotten incredibly good over the last 40 years, and the ones from around the world agree with each other. But in fact, I'm not even going to talk about computer models. I'm just going to talk about the data that we measure. So if we look at the science and we start what's happening to the air, now there are various sources of data on the temperature history. And this is the average air temperature near the surface of the Earth, both above the ground and above the ocean. This is the data set I like the best. This is from the Goddard Institute for Space Studies, NASA's data. But NOAA data from Hadley in England show pretty much the same thing. And you can see clearly an increase in temperature with time. Now, there are certain periods here. There was a period from 1940 to 1970 or so when there was a lot of air pollution causing some dimming of the sun. You might remember that in 1970 we passed the Clean Air Act, and you can clearly see the CO2 emerging from the background here. And there are a couple of periods here where we get slight flattening. You can see just recently there's been a slight flattening even though it's setting record temperatures. But the point is, if you look at the average over the long term, the air temperature is clearly going up. What about the ocean? Well, the red shows the increase in the air temperature, the heat in the air, and the blue shows the heat in the ocean. Water, of course, has a much higher capacity to hold heat than air does, and it's much less susceptible to these variations. So it's actually the ocean that even tells us more than the air. And 90% of that global warming heat is actually going into the ocean. And there's a clear trend, particularly in the deep ocean, that we're warming the planet. And the other is the ice. And the next speaker is going to show you, I looked at some of his slides, and he's got some very nice slides showing what's happening to the sea ice. And you might know that in 2007, and then again in 2012, we broke records for the minimum Arctic sea ice extent, which occurs in September. But it's actually not the sea ice that contributes to sea level. It's the ice based on land. And so if you look at the ice near the North Pole, near the South Pole, NASA has a very interesting way to figure that out. They have two satellites that are in polar orbit around the Earth. And those satellites will change their speed as they go over more massive areas. And by measuring the distance between those satellites, they can determine how much gravitational pull there is beneath. And they can infer then the ice mass in the north and the south. So this is what we have, and this is from the GRACE satellite data. On the left is the major ice sheet in the north, the Greenland ice sheet. And on the right is the whole of Antarctica, the east and west Antarctic. And you can see clearly a trend of decreasing ice mass. And not only that, but the trend is accelerating. The point is, the data clearly show we are very rapidly melting the polar ice caps of this planet. How many of you have seen the movie Chasing Ice? Fantastic. Good for you. For those of you who haven't, I really highly recommend seeing this film. You can get it on Netflix. You can get it on iTunes. This is Jim Balog. Jim Balog is a Boulder photographer. He's published a lot of articles in the years in National Geographic. And it's a film about the data he's taking with his extreme ice survey. You may have seen some of his footage at the train station at DIA. Anyway, it's an incredible film, an incredible climax. It's very well done. I recommend you see it. And you can see there what's happening as these glaciers calve off. Because, generally we don't see what's happening in the Arctic, and here you have a clear image. So what's the culprit? We know what the culprit is. The culprit is we're burning fossil fuels, we're putting a lot of carbon dioxide into the atmosphere. And so if you look at the history, scientists can drill these ice cores and pull up ice cores that go back as much as 800,000 years. And in those ice cores are little air bubbles, and those little bubbles of air. And those air bubbles show us how much CO2, carbon dioxide, there was in the atmosphere at that time. And they also show what the temperature in Antarctica was at that time. There's a way to infer that. And you can see that they track each other pretty well. And in fact, in the last 400,000 years, this has occurred in about 100,000 year cycles. And you can see temperature tracks carbon dioxide. And Bill in his talk is going to talk about the change in orbital parameters, the so-called Milankovitch cycles that lead to this variation. Now the skeptics will say, well, yeah, okay, they're in correspondence, but the temperature actually leads the carbon dioxide. And so I want to talk about that, but first I should mention we're close to 400 parts per million right now. In fact, we hit like 399.9 recently, and it varies seasonally somewhat, but we're close to 400. This is way higher than it's been for as far back as we can measure. All right, it's way higher than it's been. It's gone up 25% just in my lifetime. This is an incredible change, and it's happening at breakneck speed. It just hasn't happened this fast anywhere in this geologic history. So things really are different. But what about this correspondence between temperature and CO2? Well, this is now just looking at the last 22,000 years, and this is a relatively new study that came out in the journal Nature last year. And what you can see is, you can see the red is the temperature, okay, and the yellow is the measured carbon dioxide. And you can say, well, gee, maybe the skeptics are right. Look, the temperature goes up before the carbon dioxide. Again, Bill will explain why that's true. But here's the point. These folks said, well, this is interesting, but this is the carbon dioxide in the whole atmosphere of the Earth, and this is just the temperature in Antarctica. What if we go around the world and we try to figure out through proxies, through various fossils and other means, substitutes for temperature gauges, what if we try to figure out what was the global temperature? And for the first time they plotted it, and that's it. And the point is that as the carbon dioxide was released, there was quite a delay in the global temperature going up, and clearly we see carbon dioxide as a driver for global temperature rise. And so even today, if we stop putting CO2 into the atmosphere, there's more heating in the pipeline. There's a delay effect. There's also a recent article showing the correspondence between the Earth's sea level and the carbon dioxide in the atmosphere going back about 500,000 years. And this is it. Here's the sea level on the left, on the y-axis, and here's the carbon dioxide content on the x-axis. And you can see a clear correspondence between the two. The more CO2 in the atmosphere, the higher the sea level. So this is the pre-industrial sea level, and so if we come over here, that would be the 0 point. All right, so when we started burning fossil fuels in the 1700s, around 1800, 1850, we were at this level of sea level. Where are we now? If you look at this chart, this is today's sea level. Now, I can't just put a data point up here and say, oh, we're going to be 60 meters higher if we stay at this level. All right? Because during this period, there were large ice sheets that were expanding and contracting. But the people that did this study estimate that if we stop today, right where we are, 400 parts per million, ultimately the equilibrium sea level rise would be about 30 feet. All right? So the sea level wants to be 30 feet higher than it is today. Now, admittedly, that could take centuries, okay? So people are more interested in what's happening this century. And the estimates vary because it's hard to really model how fast these ice sheets are going to melt. We know they're accelerating, but it's hard to predict that. So somewhere between 2.5 feet and 6 feet of sea level rise is what we expect by 2100. So a little over 3 feet would be a meter of sea level rise. That's near the low end of this range. And as an example, if you look at the state of Florida today, and you look at, okay, in 2100, if we have this 1 meter of sea level rise, what would it look like? That's Florida with 1 meter of sea level rise. It has enormous consequences, that 1 meter of sea level rise, not just in Florida, but around the country. I also want to talk a little bit about extreme weather, and here's the question here. You know, a lot of scientists will point out, look, climate is not weather, and that's true. But, you know, we've been thinking about climate change as something that happens gradually. We worry about it for our kids, we worry about it for our grandkids. But what about this? Is the climate change causing the weather to change? Congressman Perlmutter kind of alluded to that, talking about the fires down south. So let's talk about that. These are U.S. June 2012 temperature records that were broken. Of the temperature records that are broken, about 90% of them are high temperatures, 5% of them, or 10%, 5 to 10% are low temperature records. It's the high temperature records that are being broken all around the world. NOAA has linked extreme weather to climate change. They estimate that the drought in Texas was made 20 times more likely by climate change. This is the Waldo Canyon fire in Colorado Springs. Almost 400 homes burned June a year ago. All right, this was the record fire in terms of damage in Colorado. It set a record. We set a new record this year. In June of this year, the Black Forest Fire burned more than 400 homes. That's 2 years in a row we've set records for wildfire here in Colorado. And as Ed mentioned, this is just from, I pulled this off the web just last Friday. 1 dead, 3 still missing in Manitou Springs flooding. And so what happens, Manitou Springs being a very close neighbor to Colorado Springs, you know, because of those fires, we're left without vegetation to absorb the moisture and to hold the dirt in place. And in fact, what we get is this combination of water and mud flowing down the canyon. and we get devastation. And I mean, Manitou Springs is a wonderful little town, really devastated last week by this flooding. The Bulletin of the American Meteorological Society, July of last year, had a special issue explaining extreme weather events of 2011 from a climate perspective. They looked at 7 extreme weather events around the Earth that occurred in 2011 and asked themselves, from a probabilistic standpoint, were these events made more likely by climate change? And I just show 4 of them here in 2011, the French drought, East Africa drought, Texas drought, and the flooding that occurred in Thailand. Out of those 7 events, only one, the Thailand floods, did they conclude, you know, this could have happened in the absence of climate change. The others were clearly linked to climate change. Hurricane Sandy. I grew up in the New York City area. That's where I'm from. An absolute record storm. This is seawater flooding the New York City subway system. Now, the New York City subway system was basically completed in 1904. So how unusual is it to have seawater flood the New York City subway system? Well, let's look. Here's the 10 top high water events in Lower Manhattan. Okay? And you can see they've all occurred since 1950. And this is a period from 1900 to 2012. None of these events were sufficient to flood the subway system with seawater. The subway system has gotten rainwater, particularly in recent years, from extreme rain events, but never seawater before. This is first time it's ever happened, and it easily beat that threshold to get seawater into the subway system. This was a very unusual event. So you might ask the question, okay, well, we had to get climate change, it's warming up, but why this extreme weather? Well, there's some interesting theories out there. This is Jennifer Francis, a professor at Rutgers University. She and folks at Cornell and other universities have developed a theory that is getting a lot of interest from other scientists. You're all familiar with the jet stream. You watch the weather and you can see, you know, north of the jet stream it tends to be cold, south of the jet stream it tends to be warm. And so here's the jet stream going around the Earth, and you can see a case here where this part of the U.S. is below the jet stream, quite warm. What's happening is this, and I think Bill is going to go into some explanation on this as well. The Arctic is warming more than other parts of the planet. And so the temperature differential between the mid-latitudes and the Arctic is dropping. There's not as big a temperature difference anymore. That really impacts the weather. That temperature difference drives the weather. So think about the jet stream as a river of air. Now think about a regular river. When a regular river flows down a hill or a mountain, what does it do? It flows fast in a straight line. What does it do when it gets out onto a flat plain? It slows down, it meanders. Okay? So in that case, we're reducing the gravitational force on the river when it gets on a flat plain. In this case, we've reduced the driving temperature difference. And so what's happening is the jet stream is slowing down and it's going into these really big meanders. Not only is it going into these really big meanders, but it's getting stationary. It's getting stuck. It's just sitting there for long periods of time. So when rain occurs, it can occur for days on end. When droughts occur, they can occur for weeks on end. Here's Hurricane Sandy going up the east coast of the United States. Now I can tell you, having grown up in New York City and Long Island, that in September it's not unusual to get hurricane-type weather hitting New York. But what it does is it typically runs up into New England or it goes out into the Atlantic. This was extremely unusual. When Hurricane Sandy came up, it just made a sharp left turn and a beeline to New York City and New Jersey. That caused a lot of storm surge. It forced a lot of water into the coast and caused that high water event. Well, what was happening is we had a very, very stationary, big meandering jet stream with a big high pressure sitting here. And when Sandy came up, that high pressure just forced it inland. And so I haven't seen any good peer-reviewed journal articles on Hurricane Sandy yet. But I can bet that in coming months we will see clear articles linking Hurricane Sandy to climate change. And of course, the ocean was a lot warmer than usual. The air holds about 5% more moisture. All those contributed to the fact that Sandy really carried a punch in terms of the moisture that it had. You hear this from skeptics. Well, okay, maybe the ones that will admit climate change is happening, they'll say, well, that's great, but we can't afford to fix it. My question is that true? Can we not afford to fix it? Is it such a big problem, we just can't afford it? Here's a study done by Tufts University back in 2008. the projected cost to the U.S. of climate change damage in various years, and I picked here the year 2025, so we're only talking 12 years from now. Their estimated cost to the U.S. economy of cleaning up the damage, $271 billion annually. That's what's going to cost us, right? $250 billion per year by the year 2025. That's if we keep on the path that we're on and we clean up the damage after Hurricane Sandy, the droughts, and similar events. So we did a study for the American Solar Energy Society called Tackling Climate Change in the U.S., and we looked at energy efficiency and all these renewable technologies. What can they do by the year 2030 was this study in order to mitigate climate change. And this is a plot, this is U.S. carbon emissions, this is sort of the path that we're on up here, increasing with time. This plot goes out to the year 2030, and you can see these are the various wedges of carbon reduction that are possible. This is the efficiency wedge. You might have mentioned when Ed got up at the end, he talked about the importance of energy efficiency in buildings. Buildings account for over 40% of our carbon dioxide emissions. If we could simply make buildings more energy efficient, we can do this wedge right here. The economy can continue to grow, and we can sort of level out our carbon emissions. And then we have here wind power, biofuels, biomass, photovoltaic cells, concentrating solar power, and geothermal. These are all these different wedges allow us to be on a path to where we need to be to make 80% or more reductions in carbon dioxide emissions by mid-century. So what does this cost? I did a study and I looked, I figured out the annual cost differential, the additional cost of this compared to conventional energy. If you add up all these renewable energy wedges, they would cost us $26 billion a year. Now, do you remember the number I said for 2025 for cleaning up the damage? 10 times this amount. So it's incredibly more cost effective to address climate change. That's not all the good news, though. If you look at this efficiency wedge, it's incredibly cost effective. It would save the U.S. economy $108 billion a year. If you combine them, we're saving $82 billion a year. So when people say we can't afford to address climate change, my response is we can't afford not to address climate change. If we don't address it, if we don't address it, we're on the most expensive path possible. So, can we do this? Here's a headline from May of last year. Germany set solar record, met half of its electricity demand from solar. Now, that's not continuously. That's at certain times of the year, but pretty impressive. Now, somebody on Fox News said, well, of course, Germany has more solar energy than we do. Let's take a look at that. Here's a map of the solar resource in the United States on the right. There's a map of the solar resource in Germany. So you can say that the solar resource in Germany is just as good as the solar resource we have in Alaska. So the point is, if they can do it in Germany, we can do it in the U.S. And I think something very encouraging is California's new cap-and-trade law. You know, they tried cap-and-trade. We have a cap-and-trade system to control sulfur dioxide emissions in the United States that's been very successful. There was an attempt in Congress to pass a cap-and-trade law for carbon dioxide. It almost made it through, didn't. California has taken the lead on this. They've looked at what the Europeans did wrong. And so far, it's looking very promising. So far, they've auctioned off, they've had 3 rounds of auctions for permits. The price of carbon dioxide hasn't been fluctuating wildly. It's gone up from about $10 per ton of CO2 to $14. In those 3 auctions, the state of California has collected close to $1 billion in revenue. That's how successful it's been in California. I guess what I'm hoping is, it's been so successful in California, as you recall, California took the lead in terms of emissions from vehicles. Maybe they'll take the lead here, and maybe we'll see others follow suit. So that's all I have. There's my contact information at the bottom. I'll also mention, somebody was talking about skeptic arguments before. I've given a whole presentation rebutting the common skeptic arguments. I did it at the Colorado State Capitol. It's on YouTube. If you go to the website Skeptical Science, it's run by an Australian physicist named John Cook. He does an incredibly good job of laying out the arguments the skeptics have and what the scientific results really are, what the journals say. And he gave a link to this presentation that I gave. So if you Google skeptical science and my name, if you're interested, you get my YouTube presentation that goes through all the skeptical arguments. Obviously, I don't have time to do that today. So thank you very much.